Welcome back. So in the first video, we talked about primary and secondary refrigerants. Now in this module, we will talk about the thermodynamic properties that are preferable, which enables some of the refrigerants to be selected for certain refrigeration systems. Okay, so we will look at the thermodynamic properties one by one. And the first property is boiling point. See, the boiling point of the refrigerant, it should be as low as possible. So the low boiling point at the atmospheric pressure is the preferable case in case of selecting a refrigerant. Okay, so why do I require a low boiling point? So if the boiling point is low, it is possible for the refrigerant to get condensed or sorry, it's not getting condensed, it is getting vaporized very easily. So at low boiling point, your refrigerant liquid will absorb heat or extract heat from the refrigerated space or from the material that is stored, and it will get converted from liquid into vapor. So if the boiling point is low, then the amount of heat that is removed in the form of latent heat will be more. So we always prefer refrigerants having low boiling points. And in reality, in the real life situation, almost all the refrigerants, they have low boiling points, and we prefer refrigerants with lower boiling points. Okay, so high boiling point of the refrigerant at atmospheric pressure, automatically it reduces the refrigeration capacity of the system. So if the refrigeration capacity of the system has to be more, that means if the heat extraction from the refrigerated space or from the storage material, whatever is stored there in the refrigerated space, if the amount of heat extracted has to be more, then it is better that the latent heat of vaporization is more. Okay, so in such scenario, we always prefer refrigerants with lower boiling point. So in the table, they have given you a few refrigerants. For example, ammonia in the atmospheric pressure condition, which is say 1.01325 bar, or 760 millimeters of mercury, or 76 centimeter of mercury. For ammonia, the boiling point is minus 33.3 degrees centigrade, and for sulfur dioxide it is minus 10. For freon 12 it is minus 29.8, and from freon 22 it is minus 41.3. Okay, and as we are following the refrigeration air conditioning by Domkonver, you can also refer to the textbook to see a lot of other refrigerants and their corresponding boiling points. I have just mentioned a few of them from the textbook by Domkonver. Okay, the second important property is freezing point. The freezing point, obviously, it should be as low as possible, because I don't want my refrigerant to freeze. So I don't want the refrigerant to freeze. The refrigerant is not supposed to freeze under the evaporator under the required evaporator temperature. Okay, and almost all the refrigerants, they have the freezing point below minus 30 degrees centigrade, and the freezing point should be well below the operating temperature of the refrigerant, of the evaporator, because say if the operating temperature range of the refrigerator is somewhere between 45 degree and minus 10 or minus 25. Okay, so I don't want my freezing point to be in that particular range. Say at minus 10 degrees centigrade, the refrigerant, if it freezes, then it is going to be a headache for me. So I don't want the refrigerant to have a freezing point in the operating temperature range of the refrigeration system. Okay, and we prefer a very low freezing point uh, in case of refrigerants when we go for cryogenic applications. So in case of cryogenic applications, we prefer refrigerants which have very low freezing point temperature. Look at Freon 12, minus 157.8, Freon 22, that is minus 160. So these are having very low freezing points, and these refrigerants can be used and they can be applied in situations like cryogenic applications. Okay, so the boiling point is supposed to be low, the freezing point is also supposed to be low. Okay, and then the important criteria is the evaporator and condenser pressure. See, if you look at the evaporator and condenser pressure, the evaporator and condenser pressure should be positive, which means it should have a positive value above 1 bar, obviously above the atmospheric pressure. It should not, but it should not be too high than the atmospheric pressure. Okay, the pressure should not be too high, at the same time it should not be negative. So I want the pressure to be positive or greater than the atmospheric pressure. In case if it is lesser than the atmospheric pressure, then you will have leakage of air and moisture into the refrigeration system. So to prevent leakage of air and moisture into the refrigeration system, I want the pressure to be above the atmospheric pressure. Okay, and then you have the, so if you look at the table, for ammonia, 2.3 bar is the operating pressure range when the evaporator is maintained at minus 15 degrees centigrade. And similarly, the condenser pressure, it is at 11.5 bar. So this guy is, let's say, PC, and this guy is PE. PE stands for pressure in the evaporator and PC stands for pressure in the condenser. So PC by PE is the pressure ratio. So PC by PE, if the pressure ratio is high, the operating pressure ratio is high. So in the condenser, in the compressor, I am supposed to compress between the condenser pressure level and the evaporator pressure level, right? So at the suction of the compressor. So if you look at the, let's take, say, for vapor compression system, vapor compression system as our example over here, just to give an example. Okay, so you know that, say, point number 1, though, that is at the condenser pressure level, and let's imagine that point number 2 lies on the dry saturated vapor line, sorry, on the saturated vapor line, and 3 is your condensation, and 3, 4 is your throttling process. See, in this case, 4, 1. So this is going to be the evaporator pressure, and this is going to be my condenser pressure. So the operating pressure level is between the evaporator pressure and the condenser pressure. So PC by PE. So 1, 2 is your compression process in the compressor. So if PC by PE is more, so the pressure ratio is more, then the power required to run the compressor is also huge. So we always try to keep PC by PE low. So we want this to be lower so that the power work input to the compressor is less, and if work input to the compressor is less, then COP will be more. Okay, so that is what we intend to do. So PC by PE, so higher the difference in the pressure levels, say this is 11.5 bar and this is 2.3 bar. So here I have the pressure ratio as 4.92. So when you have much of a difference between the pressure level, the pressure ratio is going to be huge. Take carbon dioxide, for instance. If you look at carbon dioxide, the operating pressure level is huge. Though the pressure ratio is less comparatively, say here this is 3 and this is almost 5. This is approximately 5, let's say 4.9, let's say approximately 5, and this guy is approximately 3. So we tend to feel like the pressure ratio is less over here, but look at the operating pressure. The operating pressure levels are very huge. At the evaporator, it is 23.7 bar. It is a higher pressure, and 71.2, that is a higher pressure. So these are extreme pressure levels, which makes it difficult for us to design a system where carbon dioxide is used as a refrigerant. Okay, so it becomes difficult to use carbon dioxide as a refrigerant and refrigeration system, because my condenser and evaporator pressures are huge, and then I have to design the system accordingly. Okay, so your evaporator and condenser pressure, it should be positive. At the same time, it should not be too higher when compared to your atmospheric pressure levels. Okay, so we have said boiling point should be less, freezing point should be less, evaporator and condenser pressure, they should be positive, but at the same time they should not be too much higher when compared with that of your atmospheric pressure. Then the next one, the critical temperature and pressure. So what is this critical temperature and pressure? The temperature above which your vapor cannot be condensed back to liquid irrespective of any high pressure. Okay, so after a particular temperature, you will not be able to bring your, or you will not be able to condense your vapor back into the liquid stage, irrespective of increasing the pressure level. Okay, so the same holds good for pressure also. So the pressure above which your vapor cannot be condensed back to liquid, that is your critical pressure. Okay, so the critical temperature of the refrigerant, it should be higher than the temperature occurring within the condenser for easy condensation of refrigerant vapor. So your critical temperature of the refrigerant, it should be higher than the temperature occurring within the condenser for easy condensation of refrigerant vapor, because I want in the condenser, the refrigerant vapor is supposed to get converted back into refrigerant liquid. So the critical temperature of the refrigerant should be much higher. If the critical temperature of the refrigerant is a little bit lower, and if I have reached that particular temperature, then it is not possible for me to condense the vapor back into the liquid. So I want the critical temperature of the refrigerant should be higher so that the condensation process is not hindered in the refrigeration system. So to name a few, ammonia, it has got a very high critical temperature of 132.8, which we are not going to achieve in a refrigeration system. So is Freon 12, 112.2. But look at carbon dioxide, the critical temperature is very low. It's 30.5. So in the summer, in tropical climates like India, where in the summer season you attain temperatures of 32 or 33, and if the critical temperature is 30.5, I can't use carbon dioxide in my refrigeration system at all. So carbon dioxide, that's why it's not preferred in most of our refrigeration systems. The operating conditions are huge. I mean, they are not suitable for running a refrigeration system. And Freon 113, the critical temperature is 214 degrees centigrade, and the corresponding critical pressures are also given. So in all these cases, the temperatures and the corresponding critical pressures, these are very huge. And these temperatures and pressure levels we are not going to achieve in a refrigeration system. So it is possible for us to select ammonia, Freon 12 and Freon 113 in our refrigeration system, where it is possible for me to condense the refrigerant vapor back into refrigerant liquid in the condenser. Okay, so to summarize, as we have done so far, your boiling point should be low, your freezing point should be low, your condenser and evaporator pressure, they should be positive, but it should not be too higher when compared with the atmospheric pressure. Now, the critical temperature and pressure, they should be as high as possible beyond the operating temperature and pressure of your refrigeration system. Latent heat of refrigerant. So obviously, we want the latent heat of refrigerant should to be as high as possible, because higher the latent heat of refrigerant, I am going to extract much of the heat from the refrigerated space. I can extract a lot of heat from the cold storage space, or the space from which heat is supposed to be removed. And when I have a high latent heat of refrigerant, I need not supply or pump in large amount of refrigerant. The weight of refrigerant that has to be circulated per ton of refrigeration, it will be low if the latent heat of the refrigerant is high. If the latent heat of refrigerant is high, I will be able to extract more amount of heat. So when I extract more amount of heat, it is possible for me to send only a lesser amount of refrigerant into the system, and that lesser amount of refrigerant itself is capable of removing a large amount of heat from the evaporator space. Okay. So when you have a higher latent heat of refrigerant, it reduces the initial cost of your refrigeration system. Okay. And when you have low latent heat refrigerants, so automatically you have to increase the size, because you have to send a large amount of refrigerant. Then you have to increase the number of cylinder, the speed of the cylinder, so everything increases. So we prefer a high latent heat of refrigerant. Okay. So your boiling point should be low, freezing point should be low, condenser and evaporator pressure, they should be positive, but at the same time they should not be too high when compared to the atmospheric pressure. Critical temperature and critical pressure of the refrigerant, they should be as high as possible, so that condensation of the vapor back into the liquid is possible. Then the latent heat of refrigerant should be once again higher, so that I will be able to remove more amount of heat from the refrigerant space. And so that concludes this second video on thermodynamic properties of the refrigerant system. Thank you.